in this tutorial, we're going to explore the concept of organic chemistry, and we're going to introduce hydrocarbons and have a look at naming. So the first thing that we're investigating here is the field of organic chemistry. Now, organic chemistry is a whole branch of chemistry that actually looks at the study predominantly of carbon molecules. Because these molecules are so important in our world, we do have chemists just specializing in organic chemistry. So organic chemistry mainly looks at the study of carbon molecules. So you then have the inorganic chemistry. Now, inorganic chemistry looks at ionic compounds, metallic compounds, so compounds that aren't involving necessarily covalent bonding. Okay, so organic is looking at predominantly carbon molecules. So the next definition that we have is we look at the concept of a hydrocarbon. Now, a hydrocarbon is an organic molecule composed of carbon and hydrogen atoms. So, for example, remembering that carbon can only have four bonds, this would be an example of a hydrocarbon. Another example of a hydrocarbon would be this molecule here. So you remember that carbon is in group number 4, which means that carbon needs to share 4 electrons because it has 4 valency electrons, and so it needs to gain 4 electrons from the external environment. Now, the way it does this is it shares, so it forms a covalent bond. So these are 2 examples of organic compounds as well as hydrocarbons. And hydrocarbons can have their varieties. So you could have this is another hydrocarbon. Okay, so that one has a double bond now. So it will have different properties compared to these first 2, but it's still considered a hydrocarbon. Now, the next definition that we look at, this chapter is full of definitions, especially at the beginning, is looking at the homologous series. Now, the homologous series is a whole family of hydrocarbons. Okay, so they have similar properties. Now, each component within a homologous series varies by this pattern here. So if it doesn't vary by that pattern, it's not part of the homologous series. So the most popular homologous series are alkanes, alkenes, and alkynes. So alkanes, what I've drawn up at the top there, these 2 molecules, this one here and this one here, are examples of alkanes. Now, the reason why they are alkanes is because between the carbon atoms there is only 1 bond. Okay, so alkanes have only 1 bond between each of the carbon atoms within the molecule. So you can have an alkane that's 100 carbons long, but it has to have single bonds between every single carbon. This molecule here, is not an alkane because it has a double bond. So going back here, alkanes tend to have only carbon-to-carbon bonds within the chain. Now, also, alkanes tend to be very stable. And not very reactive. That doesn't mean that they don't react. It just means that they may require more help or assistance to actually react. Alkanes are also referred to as saturated. Now, the reason why they're saturated molecules is because every single carbon contains the maximum number of bonds. So, for example, if you observe this carbon here has already 1, 2, 3 hydrogens and is connected to one other carbon there. So there is no space for more things to connect to that carbon, that central carbon there. So that term is given, is called saturated. So each carbon contains maximum bonds. And these are not available for any other reaction. So that's what a saturated molecule is. So each carbon contains maximum bonds, and they're all single bonds. Now, you'll find that with alkenes tend to have, as you can see, tend to have double bonds. So even if you just have one double bond, it makes it straight away an alkene. So even though you may have a chain of 100 carbons and the very last carbon to carbon link is a double bond, it is an alkene. So alkenes, these have within the chain. And you can have one of these double bonds, or you can have more than one, okay? And these are quite reactive. And the reason why they're reactive is because if you observe, say, this molecule here, look at this one, this molecule here, it is possible for that carbon there, one of the electron pairs can be actually used in reaction. The other one is used to hold the carbon to carbon together, but one of these electron pairs can actually be used in a chemical reaction, and therefore alkenes tend to be more reactive than alkanes. And they're also referred to as unsaturated because it is possible for another atom to be added to this. So it is possible to convert eventually an alkene back into an alkane by adding an additional atom there. But of course, then would need to be a sort of chemical reaction for that to happen. But so unsaturated because carbon to carbon bond can react and I guess absorb, attach another atom. Okay. Finally, you have alkynes. Now, alkynes have a carbon-to-carbon triple bond. Okay, so an example of an alkyne would be this. So that carbon there doesn't require any more hydrogen connecting to it, and this carbon just requires one more hydrogen because there's triple bonds. So most reactive, this one. And it's also referred to as unsaturated. Now, the formulas that these alkanes, alkenes, and alkynes have a formula which they vary. And let's first have a look at the alkanes. So I'll start off with an alkane, a very simple one-carbon alkane. Now, one-carbon alkane just looks like this. And it is referred to as methane. Now, the ending of, and we'll get to this in a moment, this is the prefix. Methane, meth stands for one carbon, and ane stands for the fact that it's an alkane because it has only one carbon-to-carbon bond. But the formula for this particular molecule is CH4. The next one is going to be this. So the formula for this is C2H6. The next one afterwards is this, which is C3H8. So you can see that between that, and then that and that, you will have to add another carbon and two hydrogens to go from that to that formula, and also add another CH2 to go from that to that. So the pattern, this is a homologous series. So this is what's known as a homologous series. We know that alkanes are a homologous series, and they vary by that pattern. Now, the formula that they have is, if I have this as one carbon, there is a formula where you can relate the number of carbons to the number of hydrogens. The formula is Cn. So whatever your number of carbons is, you can find the number of hydrogens by going 2 times by the number of carbons, 2 times n, and then plus 2. So this is the general formula for an alkane. So we'll write that in here somewhere. CnH2n plus 2. So that's the formula for an alkane. All right. Now, alkenes, if we have a look at those, alkenes tend to start from, they don't start from the very first carbon, okay? Because if you start from the first carbon, it's not possible to have a double bond. So alkenes skip the first carbon. They don't go through that. They start off with a 2-carbon molecule. So straight away you've got this. So this is the formula for it is C2H4. Then you may have a molecule like this. So that is C3H6. And once again, you see that it varies by CH2, the same homologous series. So this is the homologous series of alkenes. Okay? And the formula, the general formula is CnH2n. So we'll write that in here somewhere. CnH2n. That's the formula of alkenes. So you can once again use that to predict how many hydrogens there are within a molecule. And finally, you have alkynes, the homologous series of alkynes. And once again, you can only start from a 2-carbon molecule. So this is one example of an alkyne. So that's C2H2. The next one would be this. So it's C3H4, and you can see once again that the difference is adding a CH2 between one molecule to the other. So the general formula for that is Cn and then H2n minus 2. H2n minus 2. So those are the alkynes. We'll be using some of these formulas to predict molecules later on. So then we move on to naming hydrocarbons. So when you name hydrocarbons, it's really important to select the longest continuous chain of carbons and to name that chain. So let's work through an example. So I'm just going to write up a molecule as an example. So say we've got something like this. So CH3, CH3, really you should be showing each, if you draw a structural formula, which we'll also go through in a moment, a structural formula shows all the bonds within a molecule, so you should show all of them. Like so. And don't be lazy with the hydrogens, you do need to write them in, unfortunately. So, okay. So then we identify the longest continuous chain of carbons and name that chain. And so the longest continuous chain of carbons, you could go 1, 2, 3, 4, but that's not the longest chain. You could potentially go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it doesn't matter which direction you go in. I'm just going to make it simple and go that way. And I can see that 5 carbons, because I have 5 carbons means that it is a pent molecule. And because they all contain single bonds between the carbons, it's pentane. Okay, so that's the carbon chain. We're going to be using that in our name. Now, then we can see that we have a few groups that are not hydrogen necessarily, but are still present and attached to the longest carbon chain. These are called chain groups. Now, chain groups tend to, they are attached to the longest carbon chain, and you can see here, that's one chain group, that's another chain group, and that's another one. So they actually are non-hydrogens, and they can alter the property of that hydrocarbon. So in this case, a CH3 chain group is actually referred to as a methyl chain group. So you have to give the position and the name of that chain group. Now, the position is given by counting the number of, the longest chain, and actually assigning the chain groups the lowest number possible. So, for example, you could start counting from here, 1, 2, 3, 4, 5. Or you could start counting from here, 1, 2, 3, 4, 5. If you start counting this way, from 1, 2, 3, 4, you're going to assign these two chain groups number 3. They're going to be on the 3rd carbon there, and this methyl group is going to be on the 4th carbon. So that's 3 and 4 are higher numbers than if you started counting from the back here, 1, 2, 3. So you wouldn't count in this direction. You would start counting the opposite direction. So giving the actual position and the name, the position is given by the carbon of the longest chain that particular chain group sits on. So in this case, it's 2-methyl. And then you've got, because methyl is CH3, you've also got 3-methyl. And you've also got another chain group at also 3-methyl. So these are your chain groups. And then you know that you've also got pentane. We've already worked it out from the top there. So we don't have any functional groups. Now functional groups, if you can see, they're atoms or groups of atoms, like here you've got the carboxyl group, that alter the property of the hydrocarbon. So they can change the complete properties. You know, it can be suddenly your hydrocarbon can become soluble in water, whereas a hydrocarbon just containing carbon and hydrogen generally isn't. But with a functional group, it can become water soluble. Okay, but this doesn't have any functional groups, it just has chain groups, the ones in yellow. So what we're going to do is we're going to ignore those functional groups. We're going to go to step 3. So step 3 says if one or more identical chain group is present, include an appropriate prefix. So we have, in this situation, we have 3 repetition of methyl groups. We have methyl groups repeating 3 times in the molecule. So what we need to do is we need to assign a prefix. So we call it 2, 3, 3, and instead of saying methyl, 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 we say trimethyl. Okay, so that's organizing the functional groups or the chain groups, and then we have to present the name of the molecule in alphabetical order. So sometimes when you have more than one functional group, you can select which one needs to go first due to alphabetical order. So the name of this entire molecule that we drew up there is 2, 3, 3, trimethyl pentane. Okay, so this is the name of the molecule. Okay, so let's have a look at a few examples of sketching and naming molecules. So we'll have a look at this one. So I'm drawing a structural formula. Now, this has a double bond, this molecule here, and whenever there's a double bond, that takes priority. You want to make sure that the double bond has the lowest number possible. And so the longest chain in this case, hopefully see it, that it's this way. And you have to assign the double bond the lowest number. So 1, 2, 3, 4, 5. So that's the continuous chain. Now, we've also got this group here, which we know is a methyl chain, and then this, which is a chloro, and that's back from our functional group here. So it's chloro. So So going back to our molecule, if we want to name this, we'll need to assign the lowest number to the double bond. So it would be called, the longest continuous chain will be called pent 1 in. This 1 refers to the position of carbon to carbon double bonds. And then we also know that we have 3 methyl and we have 5 chloro. Okay, so again, the functional group, the most important one, is the double bond in this situation. So now we've put it together. We put it together in alphabetical order. So the systematic name of this molecule is going to be 5-chloro, 3-methyl, pent 1-ene. Okay, so that's an example of this molecule, of naming this one. Now let's have a look at another one. Okay, so longest continuous chain in this case, doesn't matter whether you go up or whether you go across, because in both ways you would get the same systematic name. So again, it also doesn't matter where you start counting from. You can start counting from this carbon or this carbon. I'll just go from left to right. I can see that my longest chain is propane. So this is my chain. Longest chain. And then these two are my side chains. This is one of my side chain, and this is another side chain. Okay, because they're not the hydrogens. So they are both positioned on 2-methyl, on carbon number 2, and they're called methyl. And again, carbon number 2 and methyl. You have to name them twice. So to give the systematic name for this molecule, you have to call it 2,2 dimethyl propane. Okay, so that's another name for the molecule. Let's have a look at another molecule. So generally, well, triple bond doesn't have much rotation around it, so you just draw it as a straight, as a linear sort of bond. So just keep that in mind when you're sketching them out. Okay, so the longest continuous carbon chain is this way. Now, because you have triple bond, again, that acts like a double bond in the sense that you want to assign it the lowest possible number. So you start counting from here, 1, 2, 3, 4, 5. Because if you start from the other way around, you assign this double bond a higher number. Now, to name this, the longest chain is referred to as pent 2-ine, because it's an alkyne now. It has a triple bond. And then the functional groups, or the functional groups, on the first carbon there's a chloro, and on the first carbon, there's also another chloro. So the way you would name this is you would call it 1,1 dichloro pent 2 ine. Okay, so that's the name of the molecule. All right, let's have a look at another one. One, two, three, four. See, this is not possible. What have I drawn? Okay. Already has 1, 2, 3, 4, so there shouldn't be part of that here. Okay, so again, you can see in this situation that if you go this way, you'll get the longest continuous carbon chain, right? There's 1, 2, 3, 4, 5. However, the double bond always takes priority, and so you have to make the double bond part of the longest chain. So 1, 2, 3, 4. So you can go 1, 2, 3, 4, or you could go 1, 2, 3, 4. It doesn't really matter which way you go. So you can go that way. But it's very important to, again, assign the lowest number. So 1, 2, 3, 4. Okay, so this is going to be the actual longest carbon chain is referred to as but1-ene. And then you've also got, on the second carbon, you've got this side chain. Now that's an ethyl side chain. So you've got 2-ethyl. So the name for this molecule here is 2-ethyl but1-ene. So that gives you a rundown of some of the naming techniques. Now the last thing that we need to look at is the difference between the 3 different forms of molecules. So you can have a structural formula, you can have a semi-structural, and you can have a molecular formula. So the structural formula shows, as I mentioned, all the bonds of the molecule. So structural formula shows all bonds, and they must be all shown. All bonds of the organic compound. Okay, so an example of this is what we've been drawing before. So, for example, this might be one of them. So you can't write OH, you have to write O-H, and like that. That would be an example of a structural formula. All the bonds are shown, and often you show them in zigzag format, unless there's a double bond or triple bond. Double bonds and triple bonds can't be compressed in this kind of way, they will be linear in the molecule, but single bonds can be rotating. So you just you maximize the angle between the bonds, because remember the bonds have negative electrons and they repel, so they need to be kept as far apart as possible to minimize the strain between the bonds. Semi-structural formula is compressed, but shows each important feature of the molecule. So, if you wanted to write out a semi-structural formula for that molecule there, you would first have to break this up into parts. So you'd look at, this part first. And so you can see if you wanted to compress it and not necessarily show the bonds, but just show the atoms that it's made up of, you would say CH3. Then you would look at the next part, which is this part here, which is CH2. And then again, it's CH2. And then COOH. So you write it in order, but you don't necessarily show all the bonds. Now, another thing with semi-structural formulas is sometimes you can, if you want to, you can actually write, because these are repeated twice, 1, 2, you can just write 2 COOH. It's just a way of simplifying the molecule. Also, if you happen to have a structural formula like this, sometimes in a semi-structural formula, the brackets, so writing out a semi-structural formula would be CH3, CH, then Cl in brackets, and CH3. So the brackets indicate that it's a functional group. And they can also indicate that it is a repetition. So you have to just be careful with what the brackets actually mean. Now the molecular formula is shows the number of atoms present in the molecule. So it's the simplest type of formula. So here you just count how many atoms there are. So there are there's a carbon, there's 1, 2, 3, 4 of them. C4. Then you would count all the hydrogens. So you've got 3, 2, 5, 7, 8, and O2. So molecular formula, you can see that this is the semi-structural formula, then semi-structural to molecular. Again, you've got a pattern here. The structural formula shows all the bonds, the semi-structural formula compresses them, and the molecular formula just gives mainly the atoms. So this would be C3, H4 plus 3, 7, Cl. So that would be the molecular formula of the compound.